All right. Good morning, everyone. It is my distinct pleasure to introduce our first plenary speaker, Professor Roger Ghanem. Professor Ghanem is the Tryon Chair of Stochastic Methods and Simulations at the University of Southern California, where he's also professor in the departments of Civil and Environmental Engineering and Aerospace and Mechanical Engineering. His research is in the areas of stochastic analysis and computational science. He has published more than 200 papers covering all aspects of uncertainty quantification, from stochastic modeling to propagation techniques to statistical inverse problems applied to complex multi-scale systems. Dr. Ghanem's work has profoundly shaped the field over the past 3 decades, starting with his book on the stochastic finite element method. Written more than 30 years ago, this book indeed introduced one of the very first, if not the first, operator learning architecture where Karaninov expansions are used to encode and decode stochastic processes, and polynomial chaos is used to learn the map between the reduced Karaninov coordinates. The book does not mention encoding, decoding, or learning. These are modern terms we are using now. But the ideas are very much the same. And this is just to show you how transformative Roger's ideas were and still are. In doing so, Roger contributed to make UQ a fundamental pillar of computational modeling. And to honor these achievements, he received many prestigious accolades from various societies, including EMI, ASEM, SIAM, and USNCCM18. I have no doubt that Roger's talk today will similarly spark interest and inspire many of us. This plenary will take us on a journey from data analysis, leveraging gradients to reveal multi-scale structures and transformation into latent spaces, and efficient generative models capturing measure concentration. Roger will show us how such techniques can be leveraged to gain new insight into physics, build statistical surrogate models, and characterize information gain in data collection protocols. So now please join me in welcoming Professor Roger Ghanem.
Thank you very much for your help with the projector. And thank you, Johan, for your very generous introduction. Reserve your applause to the end. So, what? Okay, good. So reserve your applause to the end. So I'll be talking about gradients, new gradients that are relevant for data exploration. It's not really strange to mechanicians, but first, big part of the talk is the result of a collaboration with Christian Schwarz that started about 10 years ago. And in the middle, we've had other collaborations with folks at GE, GM, Sandia, and a number of other universities through few MURIs. So they have provided much of the data that I'll be discussing in my presentation. The work with Christian started with this first article here, about 10 years ago, 9 years ago, and this is the most recent article in the series of papers. Yes. So these are the beginning and the current situation of these articles, of this series of articles. So the main challenge that we're dealing with, that we want to deal with, is the fact that we have little data in many cases, in most cases of interest. Data is either very difficult to acquire in a lab, or for most of the serious problems we care about, data is extremely expensive to obtain in a numerical simulation. And the numerical simulations are extremely prone to model errors or perhaps instabilities. What? To numerical instabilities. Yet, in spite of the sparsity of data, we still have to make decisions, not only make predictions, but make, can you hear me? We have to make decisions, not only predictions, predicated on the limited data. Worse than a necktie. Thank you. All right, so we still have to make decisions predicated on whatever data we have. And as a matter of fact, the more complex either the physics model or the more sparse the data is, the more consequential the decisions seem to be. Okay. Typically, as mechanicians, we are used to discovering knowledge with gradients. Right? That's the first take we have on any new set of physical experiments or thought experiments that we pursue. We look for gradients in deformation and densities and pressure and fabric and mesh resolution. When we're looking for error analysis, we pursue gradients. So what I want to describe to you is some new sets of gradients that are relevant in data exploration. These would be gradients on probabilities, gradients on graphs, gradients on manifolds, and these will help us squeeze as much information and knowledge as we can from the little data that we have. Just in the same way that we squeeze knowledge and information from experiments in order to build mechanistic models. Right? So it's not something new. Just at some level of abstraction, we're pursuing a similar exploration. So I'm going to start with a very simple example, just to drive some point. Imagine the data is on a spiral. And in this case, we have a lot of data collected on the spiral. Now, a statistical model of this data is going to look, if you put kernels on the data on the spiral, are we good? So a stationary distribution or the invariant distribution or the KDE model of this spiral data is what you see on the right. Okay? So this is the stationary distribution. So in the case where we have data with structure and we have a lot of the data, then the data has a strong signature that appears in its distribution. And what I'm going to do now is allow these initial samples taken on this spiral to gravitate. So when you leave data points in an ambient space governed by distribution, the data points are going to gravitate, be driven by that distribution. And it's a gradient. It's the individuals want to follow the collective, if you want, and they will follow the collective in this fashion. So the individual that were stationed on the spiral are being diffused and driven to the stationary distribution, okay, according to this flow here. And you observe that as this happens, the signature of the spiral is retained because we have a lot of data. Now we have a little less data. And in this case, the stationary distribution, the distribution of the collective, if you want, is what you see on the right. Contrast this to what you have in this case. You lost much of the signature of the spiral. And if you let these individuals now gravitate, be diffused towards the collective, initially they will be doing this, and then eventually they are going to just be dispersed completely by the main distribution. Now, if we have even fewer data points, which is typically the case, Now, you may not realize at the outset that you are on a spiral, but as the data starts to diffuse, you will very quickly now also reach that amorphous distribution. Okay? So the challenge is we typically don't know that there's a spiral. We know that there are physics that ties the data together. So that is some underlying structure, some intrinsic structure to the data. We don't know where it is. We know it exists. And typically, we have little data, right? And most standard statistical approaches will be driven by a distribution that looks like what you have on the right. And it will very quickly smear out whatever signature the individual data points have. Okay. So individual data points are created by fundamental constraints, whether they are the output of a numerical simulation or obtained from an experiment. They know where they have been, but they are scarce, right? The manner in which they are collected also, the organization of the data reflects some operational constraints typically. So these are also very important. The continuum, which is the other end, which is when you smear out the information, continuum is plentiful, very easy to sample, but it violates fundamental operational constraints in ways that we don't really understand. Right? So you may start here by saying that your data is positive, and by the time you're generating samples from this distribution, you are going to end up with negative samples, for example. Okay? So I make, and I'm trying to use words that draw an analogy with mechanics. We have, if you want, the microscale, the individual points, the atomistic realm, and we have the continuum realm. And what we are looking for is something like a mesoscale, right? An emerging local structure that we can count on that is somewhere between this and when we get the full confusion, right? And you can observe here at some point, here, here, for example, right? The dots connected a little bit. And if you keep going, you are going to end up with more amorphous distribution, okay? So we are looking for something that looks like a mesoscale in the data structure. Okay. Again, this is to make that point, right? So there is some point at which the dots connect a little bit, and then they dissipate again. And we observe this in many situations. So how to characterize a mesoscale? Well, structure starts to coalesce, then it dissipates. So there's a lower entropy as the data progresses in time towards the collective distribution. The entropy is decreasing because you have structure that's starting to emerge. And then at some point, the entropy starts to increase again. So the lower entropy relative to the previous step. It's one way to characterize progression towards order. And then at some point, you start to lose entropy or to gain entropy again. And therefore, the minimum absolute entropy flux is one way to characterize the step in the evolution of the data towards their stationary distribution to characterize the step associated with the emergence of mesoscale. Okay? Now, local behavior, and as we observed in the spirals example, for instance, it's not just the points that are going to give us structure, it is aggregation of points. So there's some local structure that's also important, in addition to the individuals and the collective behavior of the individuals. Now, local structure is not present in the data, in each data point itself. The local structure is present in the collection of the data that we have. Right? So this local structure is not intrinsic in the data. We have to introduce a model that says how the data jointly behaves. Right? So this is going to be an analyst intrusion on this procedure. right? And I will describe how that is done in a logical fashion. So we introduce a structural model, and then given that model, we try to identify at which step in the data progression we capture a mesoscale structure. Okay? Excuse me. So the way we introduce the structural model is we use a graph of the data. So we look at the data in its ambient space, we connect the dots, and that is our structural model. In particular, we rely on a diffusion graph that allows each neighbor to talk or to discover its neighborhood. It counts how many neighbors it has and how close the different neighbors are to that point. Right? So this graph is going to evolve with the data as it diffuses. So if you go back here, if you draw a graph at this initial step, and then you freeze the data at a later step, that graph has evolved, right? And at some later point, towards the end, the graph is going to be a completely connected set of edges and vertices that covers the whole space. So it's going to lose its intrinsic structure. Thank you very much, Lori. I appreciate that. Okay. So we use a graph to introduce structure to the data, to describe how points talk to each other, in particular the diffusion graph. And we're going, as that graph evolves, we're going to be exploring the entropy flux of that graph, okay, of the data generated by that graph. And then at some point, we're going to say, we're starting to generate more entropy now, and this is the sweet spot at which we are going to start generating samples. The samples we obtain from this particular snapshot are the ones we care about. Okay, good. So I'm going to describe, as an intermediate step, what we do at each step of that evolution of the data. So you start first with 10 data points, right? They're not enough for you to work with, right? You need 1 million data points. So what you do is, what you would like to do is allow those 10 data points to multiply. You'd want to generate samples around those 10 data points, right? So that you can perform statistical analyses. And as we said, if you follow standard statistical procedures, the samples you are going to generate will not really have this individual signature of the data you started with. They're going to be generated from the collective. It's as if you're trying to do atomistic simulations and you are stuck with a continuum that does not talk to the atoms. Okay? So at any given snapshot, we introduce what we refer to as PLUM, the probabilistic learning on manifold. So at that snapshot, we have a bunch of data, and we're going to build a graph on that data, and we're going to generate more samples at that particular snapshot. And those samples are going to tell us whether we are at a good position or not, or the entropy of that particular snapshot. So a quick start for PLUM. We discover an intrinsic structure of the data that we have. Okay. We use diffusion coordinates. So, for example, in the case of the ellipsoid, you try to discover the geodesic distance along the ellipsoid. And that's how you describe the distance between successive points. Of course, data we care about doesn't follow an ellipsoid. It's very strange data that comes from very high-dimensional experiments. But you still can carry the idea of a diffusion distance in that large data set. So once we have that intrinsic structure that we discovered through diffusion coordinates, we quantify the collective distribution, the stationary distribution of the data, and that's going to be the distribution that is going to draw the individual samples. number 2. Then as we start to generate samples from our individual points, we project those samples in a Galerkin scheme on that intrinsic structure. And that gives us the ability to generate a large number of samples that are as close as possible to the target distribution while being constrained to remain on the intrinsic structure. Okay. So let's go through the steps a little bit in more detail. So the first step is you start with the data matrix. Let's call it X. Right? The number of rows is the number of samples you have, typically very small. The number of columns is the number of features you have, typically very large. Okay? And the first thing we always do is we apply PCA to standardize, to normalize the data. So H is the matrix of normalized X. And we build, now H is a matrix, so we build a probability distribution on that matrix, obtained by multiplying the probability distribution obtained for each individual feature. So this is an important step here. It says that our sample generation scheme, at every step, rather than generating one sample of data of stress or strain, we're going to be generating a replica of the initial data set. So every sample that we generate will be a replica of the full initial data set. It will be a replica of the data we started with, X. And we build P sub H for each feature is built using kernels like this, where P sub nu is typically a Gaussian kernel. And the matrix measure is built as a product measure on the n data points. So the n data points are assumed independent, and in this fashion, we build the matrix distribution. Okay. So once we have this, this is our right-hand side distribution. Now we start sampling. We build an E2 equation that's going to drive the individual points. Excuse me. So this is a standard E2 equation that says if we drive this equation with a potential L, and L is related to Q in this fashion, some function Q in this fashion, then the samples Z are going to have a distribution Q. Right? So this says if you drive this equation with particular potential, you can shape the distribution of the samples you are generating. Right? And typically, we want this here, Q, to be our target distribution. And you learn the potential, and that will allow you to generate samples from the target. This is a continuous version of Markov chain Monte Carlo. So if we do this, and we solve that equation to our best of our knowledge, we're going to be generating samples from the collective distribution, which is not what you want. Right? Because we built Q to be the collective distribution. So rather than doing this, we introduce a good matrix, P, right? And we find the eigenvector of that good matrix. I'll tell you what a good matrix is in a little bit. And we limit ourselves, or actually we don't limit ourselves. We're going to do a Galerkin approximation, a Galerkin solution of the E2 equation following these eigenvectors. Okay? And what does that mean? That means that we replace Y and Z by the approximations on the basis set, and we project the error on that basis set. Right? And as we increase the size of this approximating space, we're going to converge to this previous solution. So the new samples now, however, if we limit ourselves to the first m vectors, the new samples are restricted to the span of G, which are the first m eigenvectors. As m approaches n, as we take all the samples, we are going back to the original paradigm, which is not really what you want. Now, if the good matrix that we have has separation in this fashion, these are its eigenvalues, then we can treat the contributions from these eigenvectors as noise, and contributions from these guys here as whatever helps us be localized on the structures that we care about. Okay? So we look for a matrix that has this behavior. And it turns out that if we follow, if we select a diffusion matrix by choosing a diffusion kernel or some positive definite kernel, building a matrix on that kernel, normalizing the matrix so that it becomes a transition matrix. So now if you take the sum of the rows of the matrix and you pre-multiply K by the sum of rows, suddenly that matrix becomes a stochastic matrix because the sum of its rows is 1, which means that it describes a statistical, a Markovian transition on the graph provided by the data. So when you take B inverse times K, this matrix here now is a transition matrix on the graph of the data. And that comes with some very nice properties. You solve the eigen problem of this matrix P. It's non-symmetrical, so care has to be taken solving this eigen problem. And we end up with the eigenvectors, and the eigenvalues of that matrix will always have this type of behavior. Okay? Good. So that's a good matrix. You take a transition matrix on the graph. It's going to give you behavior like this. And then we come back to the projected Ito equation with G being limited to the dominant eigenvectors of the transition matrix. And this is very quick to sample from. Typically, we start with very few samples from which to build this Lagrangian here, this potential here. And once we have this equation, typically we generate thousands of replicas of the initial data set. And those replicas share with the initial data set that they belong to the same span of G sub M. Okay. And they're also as close as possible to the target distribution while being restrained to that span. And once you have all of these distributions, all of these samples, it's straightforward matter to carry out conditional expectation. So the expected value of some quantity Q given W can be obtained. Well, this is a standard expression. The problem with this expression is that N needs to be large typically. And if you have very few samples, you're stuck. You cannot evaluate this expression with any accuracy, right? So what this says is that Q, the expected value of Q, is obtained from the samples you have for Q, each of them weighed by how close the associated W is to the conditional W. Okay? And if this N is not large enough, then this is not an accurate representation. So with the procedure I described before, that plum procedure, we can increase this N to whatever value we want. Okay. Now, in addition to the expectation, conditional expectation, we have also an expression for conditional distribution. Right? So in addition to calculating the expected value given some condition, we can get the full distribution. And that's very important for many things that I'll be talking about in a little bit. All right. So this is what you get from having a very few samples at a given snapshot. You discover a manifold within that snapshot. You generate many samples that are informed by that graph and the manifold. Now, how do we connect this to the transient case I had before? Excuse me. Connection is very tedious, and it required some very astute mathematical genius from Christian to dot all the I's and cross all the T's. The key insight is that the diffusion kernel that I described before is equivalent to a transition on the graph described by the data, as I mentioned. And that ends up being related to the eigenvalues of the Fokker-Planck and eigenvectors of the Fokker-Planck equation. Okay. We don't have to go into the details of that, but a key insight from following all those steps is that the action of this kernel at any given time t can be obtained by taking an average over the samples. So if x are the samples that you have at any given time step, u and v are functions on the data, then the action of k on u and v can be obtained by applying it to the data set and taking an average over the data set. And this estimation here ends up, you can show that you get almost true convergence, and you have an unbiased estimator for this quantity here is an unbiased estimator of the actual KTU comma V. Okay. So this is the key ingredient that enables the implementation to the transition to the transient case. So I'm going to go through a number of examples to show the value of what I just described on a few problems of great interest to us. First one is a nuclear power plant, nuclear waste management. So these are waste gaskets. You cannot open them. They have nuclear waste in them. They're going to be transported from their initial site to some final repository. And one is typically concerned in the damage that happens to the internal components during transport. And the way you can tell whether it's damaged or not is you ping it on the outside, you listen, and it's an inverse problem, typically, right? So what we did is we had the blueprints from a company that built these things, and we built a very highly detailed model, finite element model of this. It's about 200 million degrees of freedom. It has a basket here. The basket has room for 64 assemblies. Each assembly looks like this. No, the assemblies look like this here. They have room for 91 fuel cells, fuel rods, right? And these are all put together in here. And interspersed between them are water coolants and supporters and springs and whatnot. Okay. So the model has 200 million degrees of freedom with 64 assemblies, 81 fuel cells per assembly, and we have about 500 random variables describing all the connecting elements, the springs between the fuels, the baskets, and the casket. And what we're interested in, but when you ping and you listen, you're collecting the FRFs, right? The frequency response function, which is the frequency transform, the Fourier transform of the response normalized by the input. Actually, we'll be looking at the modulus of H. Okay? H now is a function of frequency. Because we don't know the springs connecting all the components inside, we don't have a deterministic model. And we don't know if some of them are damaged as well, right? So H is going to be a random function. And this is the typical FRF. What you get, the solid green is the average FRF, and the scatter around it is FRF obtained by varying the springs and the supports inside that very fancy model. So there's significant scatter in the FRF. Now, typically the damage, internal damage in these components that we care about is small damage that has a signature in the higher frequencies, right? And is difficult to detect in any experiment. What you can detect reasonably well in an experiment are the low frequency components. But we care about damage. Low frequency are important clearly, but they're easy to detect. But we care about measuring the blue and inferring the red. Okay? So what we do in this case is we build a large matrix. We call the red Q. We call the blue W. And we want to predict Q given W. Okay? We have a big vector of Qs, a big vector of Ws along the frequencies. We have measurements obtained from several experiments, numerical experiment in this case. But we cannot afford to have many of them, just about, I don't know, we did make 500 numerical experiments. But the dimension of this is about 1,000, right? You go from 0 to 1,000. You condition on 500 of them, and you want to predict another 500. So we are in a 1,000-dimensional space with only 500 samples. So we augment those 500 samples with Plum, I described before. We obtain about 5 million samples. Right? That's what I said. And this is what we predict. So these are examples of test cases. The red band is the probability distribution obtained from Plum. Right? So we're predicting the probability distribution of that function. And what you see in the middle, that blue dotted line in the middle of the red zone, that's the actual data associated with that test case. Right? So with very limited data in a huge dimensional space, right, we are able to make some really very fundamental predictions. Right? Very small training set for such a dimensional space. Okay. Good. So that's one example. Another example is related to power. By the way, this was a collaboration with a colleague at at USC, Bora Jensturk, and a number of other people through a NUEP-funded effort. This is a power grid example. This is collaboration with people at Sandia, Cosman, Safta at Sandia, and John Paul Watson at Livermore. So we want to anticipate blackout over a power grid, okay? And compute mitigation actions. So we have a toy problem that we worked with. It's this toy problem here. It has 118 buses and 321 generators. Buses are, generators connect to a bus, and demands are provided at buses, not at generators. Okay? This is the actual diagram. Okay? And this is supposed to represent California, with Southern California, the Sacramento area, and the Bay Area in different colors. Okay? And what I'm going to show you just very quickly is a focus on, well, first of all, anticipate blackout. What does it mean to blackout? How do you anticipate blackout? The initial attempt was to relate blackout to extreme weather, predict weather, and then come back and say extreme weather will cause blackout. Weather is very complicated to characterize, right? So we switched gears, and after we looked at a lot of data, we discovered that, well, the cost associated with production has that shape. And we were thinking that perhaps blackout means we can no longer afford to provide power. So the closer you are to higher cost, the closer you are to blackout. So we proceeded with that model in our head. And we built a cost model from some data that we had. Okay. And what we're seeing here, I'll explain the dots in a tiny bit. And I'm going to be focused on one or two, perhaps, of these generators, or buses, actually, in this case. Okay. So what we did is, oops. Do I have it here? Oh, sorry. There was more here. I didn't see it. I'm careful enough. Do I have a subscription? Yes. Okay. So we have that many buses, that many generators, and we had training data from a full year, 365 days. Now, the training data has both the demand, the generation, has everything. Okay? But it doesn't have the cost. So what we did was the following. We took these 365 data points. We took the demand, no, we took the demand from them. We fed it into an optimization code, POMO, which is standard in the electric power industry. And for each day, we ended up computing the optimal generation schedule over 24 hours. Okay? And for that, we get the cost, right? Because we want the cost. So for 365 days, we had demand, generation, over 24 hours each. We had the ramp up, the ramp down. We had a lot of other intermediate functions that come from optimization, all the what are they called? All the intermediate variables. We don't have to worry about those. But needless to say, we had about 600-dimensional problem with 600 features and only 365 data points. And our interest in this case was the following. We wanted to say, if we have a cost at this level, what is the distribution of generation over the whole network? Not only over the whole network, but over the whole day, per hour, over the network. And then we switch. We say, as we increase the cost, how does the cost map back to how the generators turn on or off over a whole day? Right? So this gives us a tool to explore what happens as you get closer and closer to extreme costs, which generators get closer to the limits, and we're calculating a mitigation strategy to tell managers of those generators to be careful, for example. Okay? And this is what we get. This is an example of what we get. Here I'm looking at, again, I have 10 values of cost here, and I'm looking at production at this bus. Okay? Now, we have similar things for all the buses, but we don't have time to go over that. So what we have is the following. Over here, I'm looking at 5 conditions associated with the low cost, these 5 low costs. And this plot here, I'm looking at conditions associated with the high costs. And in this particular case, I picked it because it gives us some non-intuitive, non-obvious results. You see, for example, that one of the costs, not the highest cost, this is the, actually no, this is the brown one, this is the highest one. But if you look at this red curve here, it is some intermediate high cost. It's some cost here, can be associated with extreme generation at that particular bus. So there are some non-intuitive results that one can get from analysis like this, given the complexity of the system and the complexity of the power exchange between the different generators and buses. Okay? So this is, again, just a snapshot of what we're doing here. Again, in this case, we're conditioning on Q, on the cost, and we're predicting 599 variables that are the generation and demand at all the generators. Okay. And we had to go from 365 samples for training to a few million samples for prediction. Finally, just very quickly, this is another very interesting example. Lifing of, this is a collaboration with colleagues at General Electric and Pittsburgh. And this data came from Pittsburgh. This piece here is meant to go inside a hydrogen burning engine. And we were studying the effect of hydrogen environments on the embrittlement of these materials. So this piece sat in an oven in a hydrogen environment for 900,000 hours. This is what the specimen looks like. And then under, Okay, so it went under an X-ray tomography, and we came back with a lot of the data about how deep the oxidation went and all the morphology of these specimens. Now, we only had about 50 specimens like this. But what we wanted to learn was discover some insights, some relationships between how deep the oxides go and how deep the oxidizing layer forms at the top, for example, or the width of the detachment zone between the oxidizing layer and the substrate. So there are many features that are captured in the X-ray tomography that gives us variables that do not typically close under energetic considerations. So you cannot write equations that control those variables. But common sense tells us that if you observe one, you get sufficient information about another one, not necessarily through a physics equation, but through a joint statistical model. And that's what we wanted to discover. There was a picture here that showed the details, but that's fine. So we wanted to discover fundamental processes leading to embrittlement, and this is an example of what we get. So we have about 10 features that we observed in those specimens, and the features are, for example, the thickness of the oxidizing layer, how deep the oxidation goes in the domain, the net area of the oxidizing dots in the domain, right? So we have 9 total of those features, and we have about 90 or 100 specimens. Not enough to make any inference. So we went with 100, generated 1 million samples, and what we have here is the following. We want to predict the microvoid depth, how deep the microvoid goes in the material. And we are not sure, because we're fishing for knowledge here, right? We don't know yet. We're not sure which observables are critical for predicting the microvoid depth. We have our 10 features, right? So we divided the 10 features into, we took the power set on them. We conditioned on each one of them individually, conditioned on them pairwise, 3-wise, 4-wise. We took all possible combinations, and that's what these W's mean. Here I'm conditioning on the 1st, 5th, 6th, and 10th feature, for example, and that's the probability distribution of the microvoids when I condition on those features. When I condition on other features, we get a different distribution. And what we observe is that some observables, rather than helping you, introduce noise in your ability to predict. There are some features that unless you have them, you cannot predict. Right? So this is a scientific exploration that we are able to carry out with, it's a statistical exploration, but it requires a large amount of data. And 100 samples would not allow you to even scratch the surface with this. Right? So capabilities like Plum allowed us to expand the number of samples and carry out these. And you observe the dot here, the red dot here, is what happened on that particular experiment. And we are not very far off in our predictions in most cases, except for some observables, we are completely off because those observables serve as noise. Okay, as conclusion. Okay, so with advances in sensing manufacturing, we are increasingly faced with problems for which we don't really know the physics, like this last one I described to you. Physics is too complex to describe we understand how atoms interact with each other, but taking this to the device scale, we don't know what happens at that scale, right? But the data knows where it has been. So if we know how to talk to the data, right? It can tell us where it has been, perhaps. But it requires slightly new language for us to interact with it. And what I tried to highlight really very fast is that there are issues of infrastructure based on graphs, how the data connects in some ambient space. Intrinsic structure, I described manifold as an intrinsic structure, and the ability to understand how the data is drawn to a collective is also important, right? And I think that's it. Thank you. Sorry.
All right, so we will have to stop in like 5 minutes to stay on time. So I'd like to open the floor for questions for Roger.
Yes.
Do we have like a...
It's coming.
Thank you, Roger. Very nice talk. So a question I have is, okay, so you don't have too many data, and you want to generate more, so you can do a better prediction. So your first thing is you try to discover the manifold, so you can generate data. And then you mentioned that you wanted to have so entropy cannot decrease, entropy has to increase. Where did you impose that condition?
Yeah, that's right.
Where Hamiltonian?
That's right. So in trying to calibrate this kernel, that means we didn't have time to talk about everything. But the choice of this kernel is related to entropy. You try to choose the epsilon, for example, in a way that says, this is the kernel that gives me the most structure in my data. Right? Okay. This is one place where it appears.
Hello. Have you published this and where can we find it?
I'm sorry?
Have you published this and where can we find it?
We have 10, 15, 20 publications, I forget. Yes. If you Google, I've listed 2 publications here. The first and the last, okay? But there are many publications in between. And Professor Suarez has published additional papers as well related to this.
Hi, thank you for a wonderful talk. So my question is about sort of the last portion of your talk and trying to interpret the results. Sorry, right here. So you'd mentioned that some of the samples that it generates are replicating the noise and therefore aren't valid, whereas other samples that your model is generating are really informative. How do you discern that?
No, I did not say that. I said depending on what conditions you take, and the way we discern that, not samples, depending on which conditions you take. For example, if you give too much weight in your observation to the volume of microvoids, you may end up completely losing predictability. And we know that by comparing these distributions to the actual data point that we have, right? This red dot on the x-axis is the ground truth. Okay, here. Well, on these plots, we have a red dot on the x-axis. That's the ground truth. And sometimes when we add a certain observable, we completely shift away from that red dot. And we know then that observable, if we include it in our introspection, if we include it in our analysis, we're completely off, which means the information from that observable is leading us astray. We're missing, remember, these variables do not close under any physical system. We are not allowed, we are not permitted to write a physics equation that relate those variables, right? So we're missing, there are many hidden variables that we are not even looking at. That could explain why some variables may seem to be noise,
Okay.
right?
So are you using that then to inform the model in those spaces where the red dot is not in your...
That's right. We're trying to understand our objective eventually here is to build some kinetic model that can be used in design, right? But we want to know which variables to include in that kinetic model and which variables to avoid including,
Right, great.
given that these are the only observables we have.
Okay, thank you.
All right, so in the interest of time, we'll have to stop here. Let's give Roger another round of applause.
Thank you very much.
And I do encourage you to reach out to Roger should you have any questions or discussions with him. Thank you.